and this is key to understanding channels. Hello everyone, I'm João and welcome to Jesk. There has never been a time where we discuss data as much as we do right now. In software development, we can't get enough of talking about streams, data traffic, scalability, and performance. Not always, unfortunately, and parallelism even when there is none. At least not in a direct way. And we almost always land in the same discussion. We talk about it, we argue about it, and we say it multiple times. We need data streaming. But what is data streaming? Just some data going from here to there? Do you know what it is? Do you? If you do, then I have a suggestion for you. Click on the link in the description for the next chapter. Otherwise, please bear with me. We will have a look at data streaming right now in this chapter. Although generically speaking, we can say that data streaming is just sending data from one point to the other, data streaming is per definition a process of transmitting a flow of data as a sequence to deliver value on the consumer side. There are multiple ways to do that. However, the basics of data streaming follow a few principles. Let's start with an example that is very analogous to how Flow, Flux, RxJava, and Java streams work. And bear with me on this. Trust me. We start with making coffee. When we are done with coffee making on a French press, we need to wash our glass cup, which by now has some moist coffee grounds. We want to use these coffee grounds to make some sort of fertilizer for our plants. But we don't want to scratch our glass cup, and so we fill the cup with water. Stir it up, drop the content into a drainer, and at the end we get the coffee grounds on the drainer, and we can use that later. If you didn't notice yet, the coffee grounds represent our data. In this case, the water is our stream and the glass cup means nothing. However, as we will see later on, we could also say that the glass cup is analogous to a channel. What I want to illustrate is the idea of the role of water. The water flows or streams only in one direction. When the coffee grounds get drained, we can't put them back in the glass jar in the same way we took them out. In other words, the exact reverse is not possible. This also illustrates that these kinds of streams are not reusable, and that they never contain data. Since these streams do not hold data when completed, and they terminate once all operations are complete, they are also known as cold streams. Such cold stream, or also referred to as cold data source, my favorite, also applies, so it seems, to sequences. If you don't know what a sequence is, in general terms, this is something we use in code to provide a collection of elements on demand that have been calculated applying a formula to the current and previous value. An example of this would be if we want to predict how many hogweeds, giant hogweeds, would grow in a small area if left unchecked. A growth model for this would definitely result in very high numbers for the first elements, but it would give an idea of how this plant could proliferate in certain areas. This would not necessarily result in a geometric progression with the calculus in this sequence, but this is just to say that an engineering model could be applied to it. Sequences are known as cold data sources for the same reason as streams are called cold data sources. They never get to hold any data, and they also terminate their function after usage. We just talked about cold streams. As you can imagine, there are also hot streams. And before we understand what they are, let's talk about canals. And again, trust me on this. First and foremost, what is a canal? Is this a canal? Is this a channel? Is this a canal or a channel? If you are not confused, then that is great. And if you are, then I have to explain you the difference. Both a canal and a channel are bodies of water that stream water pretty much in the same way as a river does. The difference is that canals are artificially made and channels are made by nature. And for the most part, they separate two larger bodies of water. This is important to distinguish in English because in other languages, like Dutch or Portuguese, there is no distinguishment between channel and canal. For both terms, the translation in Portuguese is canal and the translation in Dutch is canal. Although the terms are used interchangeably, they are quite different. One example of a channel is the English Channel, And an example of a canal is basically any canal in Amsterdam or other Dutch cities. In all of these examples, we see one thing in common. And again, that is the water stream. For these canals, we will talk about boats, much in the same way as we talk about data. Boats will be our data, the water our stream, and finally, the canal will be a parallel to our channel in terms of code. Just as much as in the example of the coffee made with a French press, we said that the glass would be analogous to a channel. However, in that example, the glass was merely a container of data. We can even say that the coffee grounds were contained in a list. Every single particle is an element of that list. And that list, and any other collection for that matter, is also classified as a hot data source. And this is purely because they can contain and keep data, but they don't stream it. We can take elements out of it, but every time we do that, the collection changes. So in coding terms, we took a data source, our coffee grounds, created a stream, and pushed the grounds through the ladder. But they were never kept in the stream. We can't hold values in any of the cold data streams discussed in the beginning. We can, however, hold elements in a hot data stream. And this is key to understanding channels. When a boat sails through a canal, it usually does that in one direction. In our example, a boat is driven through the water along with the direction of the current. The canal has the boat, and the boat will eventually dock at the end of the stream. This is the collection point, or in other words, where we receive the boat. If the boat wants to stop in the middle of the way, it can do so, and in that case, the canal is holding it. Boats shouldn't enter freely these canals, and normally they don't. If there are too many of these boats, we can't possibly navigate. Regardless of possible restrictions and regulations, we know that after a certain point, if the canal is full of boats, nobody can navigate through it, and it can become quite hazardous to do so. But we do have an empirical concept on how many boats should go in, right? That's a buffer. That number is a buffer, and we can't control that buffer. No boat is allowed in until the pier receives another boat on the other end, once that buffer is full. A channel is, because of all of these reasons, and just like the collections, considered to be a hot data source. And because it streams data, it is also considered a hot stream. And at this point, let me clarify one important thing. The visualization of what streams can look like by comparing them with the flow of water doesn't mean to say implicitly or explicitly that going down the stream is a long process. The process of streaming is normally as fast as a machine can process it, and therefore going down the stream is for the most part an almost instantaneous process per element of data. So we went through an example of cold streams with our coffee grounds and hot streams with our canals. And remember that the main difference is that cold refers to things that cannot hold data, and hot is how we shortly describe things that can and do hold data at any given time, minus the very insignificant streaming time per instance. In this next chapter of this video, we are going to fill in the gaps in the library application. This will not be just a funny example, this is actually something that could be implemented in reality. There is much more to learn about channels, and we will have a look at that in the code. Let's go hands-on code. So now we are going to have a look at the code, and we're going to see how channels actually work, and we're going to see it in action. So the first thing I want to explain to you is I have made an application, and this application is a library, and it basically what it does, it manages the books, and it's just at its recent start. And the requirement is basically about creating a system that will calculate how many pages are going to be read. It's going to measure how many pages are going to be reserved. This is on the basis of how many pages a user is going to read when they make a reservation of a book. In this library, we have different books, and we're just going to implement one endpoint. But let me just show you how far the implementation of the service for this library is. So we have here the Docker files. We have here a Postgres database, and here we have the configuration of the Postgres database. Now this is not important for the demo, but it's just to give you an idea of what we wanted to implement. This is one thing. The other thing is I have already created here a controller. So this is a Spring Boot application. This is the Spring Boot launcher. And here we have the library channel application. And this is going to start a service where we are going to make available a REST controller. Essentially, this is going to be located at the root of the service. And here we're going to receive these objects that are reservations. So Per book, a user is going to make a reservation for a certain book. This could be online or even in the library. And the reservation has, just for a matter of having an idea of what it is, a reservation has an ID, a user, a reservation date, a return date, and a book. So we are going to reserve this book. We are this user. This is our reservation date, and this is when we need to return the book. Our user in this prototype is being persisted in a database with a name, an address, and a telephone. And the book is simply being registered with an ID, with a name, and of course how many pages it has. This is ultimately the value that we are looking for. Let's have a look at what happens when we send a reservation request. When we send a reservation request, we simply receive an acknowledge, and in the background, this is going to signal to this book service that the reservation has been made. If we look at signal reservation, that is going to use the IO dispatcher in another coroutine scope, and it's going to send an asynchronous request to stats channel, and it's going to wait for it. We're going to send a reservation stats channel, and with this send method, we are going to make it reach our stats channel. Our stats channel is here defined as having an unlimited buffer. If we look at the implementation of unlimited, unlimited is the max value of integers. Technically is limited, but a max int is high enough. We also have here, we can see a result channel. And the idea behind this result channel is simply to receive all of the books that have been reserved and get the pages out of it. Essentially, we are going to map book to book pages. So the idea here is that we are going to map the book to book pages. If you know a bit about channels, the methodology that we are using now to send the books to this stats channel, this is called a fan in. This is a busy library, so people are sending a lot of requests to reserve books. And by doing that, what is also happening is that we are starting a lot of coroutines that are going to send all of these reservations to one single channel. We are sending a lot of objects to one single channel. That is called a fan in. What this channel is now going to do is going to receive all of these entities. And then we are going to start an extra of 10 coroutines that are going to receive all of these books from one single channel. And we are immediately start another form of processing data through a channel, which is called a fan out. So a lot of coroutines are receiving entities that were placed in the channel. When these coroutines all receive this data from the books, they're going to extract just the number of pages. They're going to send the number of pages through another channel, and that is the result channel. If a lot of coroutines are sending data to one same channel, you already know that. That is called a fan in. By fetching in that data, now we have a channel that contains all the number of pages. The result channel is also unlimited, and this is for a reason, because they're going to be on all the time and they're going to receive data all the time. To perform a to list on them makes no sense. There is one thing that we can do in a channel, and that is to check if it is empty or not. If it is empty, we don't do anything, and if it's not empty, we keep receiving data. There is a to-list method. If these channels contain an unlimited buffer, that also means that a to-list would hang in there forever because we don't ever get to the end of the stream. So what comes here next is a rendezvous process. This rendezvous process means that whilst an element is in the channel, the coroutines that want to send entities to it will be suspended until another coroutine receives the data from this channel. But this also means that the channel is aware when it is full or when it is empty. And this is why when we use receive in this case, and we create a to-list for a rendezvous type of channel, the code does not hang. In fact, it calculates correctly the sum of the pages, and we are able to print it out to the console. So let's recap. We have a fan-in operation to put all of the raw data in a channel. This is the stats channel. Then we use a fan-out operation to get the data out of the stats channel. Then we use another fan-in operation to put all of the data in the result channel. And then finally, we do a rendezvous operation to get all of the data out of the results channel and turn that into a list. This rendezvous channel is what we have here that is created with produce. So this produce function here, it creates a channel. And underwater, we can immediately call a to-list and a sum. We don't really see the channel, but this whole thing here This is the channel. And this is my example on how to let you know how channels work. Remember, this video has been about transmitting the idea of what channels are and how they actually work. Channels, if you have noticed, it's kind of implicit in what is being said here, but it's important to also mention it explicitly. Channels handle data in a sequential way. There is no parallelism. We can do parallelism after the channels, but channels do everything sequential. And there's no concept of broadcasting, like for example, it would happen with queues. Channels also are fair. So if you were concerned at this point in thinking, hey, if we're throwing here 10 coroutines, is one of them going to be left behind and not being used at all? All of them are going to be used because this is how channels work. If coroutines are waiting to receive data, they are going to receive the data fairly among all of them, and we're going to be able to send data from coroutines to the channel in a fair way. So that's why we say that channels are fair. We had a look at how the code is settled. Let's just run it. So now it has already run one time, 1 minute has already passed, and we have 0 pages. I'm going to use my scratch pad here, and I'm going to launch 1 time, 2 times, 3 times. So every single one of these reservations that I've sent has exactly 999 pages. So we should be getting a result of 3 times 999. Let's see if that's true. We have to wait 1 minute. There we go, 2997. So this is 3 times 999. So as you can see, the calculation has been made. And just for a recap, what happened here is that we've sent 3 times our reservations. So these reservations, at the moment, they don't have any constraints, so we can send 3. And these 3 were sent to this channel. This channel has just picked up the pages and sent the pages to another channel, which is this channel, the result channel. Once the result channel had all of this information, we then proceeded to one rendezvous channel, to where we send all of the entities until the result channel is empty. So while this is happening, we are calling toList. toList will receive calls to the result channel, gather them all together in a list, and then at the end, we sum all the results up, giving us the total 2997 pages. Have a look in the description to find the location of this module and to find my project on GitHub. My GitHub handler is j.esperancinha/Asensai the Right Waff. Alright everyone, so this video was the video I had for you about channels. I hope you've enjoyed it. I hope you've learned something about channels and how they work, streams, hot streams, cold streams, and how all of this data streaming systems can work, and maybe you found an idea to adapt it for your case. In the meantime, I hope you've enjoyed the example. I hope you didn't think that the examples are too crazy. The idea of using water as an example for streams, I made it because I think it's something that maybe something easier to understand. If you think this video has been useful for you, and if you have any suggestions or would like to comment more about it, or if you want to see me talk about anything, please let me know in the comments below. Don't forget to subscribe, leave a like, and until the next video, keep it graceful and stay sharp. Thank you so much for watching this video, and I'll see you next time. As a short disclaimer, I'd like to mention that I'm not associated or affiliated with any of the brands eventually shown, displayed, or mentioned in this video.